Binder turn in, excellent. So, it helps if I have the binder in class. That's always useful.
I think it was on the final with the best Did you do? I wrote on my final paper thing that I had. Like it's from. I can tell you the exact time. Is that when our final? Like when we present. She must have had it on the paper. December 13th from 3 to 5 p.m. So what our normal class is. It's a Thursday.
Yeah, so finals, I have a final schedule for my classes posted up here. You are Geo 102, and that means that and it's also posted outside my door. And you're also welcome to ask me. I am not one of those people that freak out because you ask something about, like, when was it due or something like that. I might tell you where to find it so you know in the future, but I'm not going to freak out on you if you have a question. So, yeah, our final for this class is on the 14th, which is a Friday. And it is at 11 o'clock in the morning, so it's pretty close to the time we actually start class, which is 11:15. Starts at 1 p.m. 2 hours are scheduled for it. You're almost certainly not going to need that much time, but you are welcome to take that time and more. I'll be posting in the next day or two a final exam week schedule for myself because it's different than during the regular course, and you're always welcome to come down, ask questions during office hours, all of that kind of good stuff. Other than the final, what's the other important thing that happens at the final? Like, what's the other thing that you do? Let's turn in. So if you have anything that's late, everybody gets one, okay? So if you have, and that can even be, if you're not turning in a binder, it can even be a term paper if you didn't turn it in at all, okay? I'm not going to recheck it at this point, but if you've got a blank where term paper is and you have no binders, you got to pick which one that you're going to do. Remember, it is important that you pass the binder section of the exam of the class because, as it says in the syllabus, if you don't pass that, you don't pass the class. So you don't want to get an I or an F depending on the situation, what led to you not to turn in the binders. Does that make sense?
If you don't have anything late, do you still want us to turn our binders in?
No.
Oh, okay.
If you have nothing late, keep your binders.
Okay.
I usually, if you want to pick up your binders, you can pick them up until the end of finals week, or I hold on to them in the first week of classes of the next semester, at which point now they have to go into the recycle cycle system and it becomes the next semester's, oh look, there's free binders, yeah, freebies. Which you can see that a lot of students choose to do that. I know you, Catherine, had a question about graduation and tickets.
Yes.
Yes, so, and I know a couple of you are graduating this semester or in the spring semester. So there is always, if you don't have enough tickets for all the people that you love, first of all, there's always an overflow room that everyone can go to. It's a live broadcast, and that means there would be live broadcasts in that room, and then afterwards, what they would do is you could still go to the little cheese and, it's not really wine, but cheese and juice reception at the other, it doesn't sound as nice as cheese and wine, cheese and juice reception at the end. Because this is America, and I don't know why we're hung up on that. In Europe, they'd be like, drink beer at 14. Yeah, no, a different universe, very different universe. I would not give a 14-year-old American a beer. So that you have that, and then on the day of, contact the bookstore, because if people know they're not everyone's showing up to graduation, there's extra tickets sometimes available. So if you want everyone to be able to sit together, so you never have to worry, everyone you love can show up, they just can't all fit in the auditorium necessarily. But sometimes there's extra tickets, students donate them if they know they don't have all the people coming. And the day of the graduation ceremony, sometimes even if you don't have a ticket, if enough people, if there's room, they'll let more people in.
Okay.
So does that help?
Check at the bookstore, yeah, okay.
Right, check at the bookstore.
So you get the tickets at the bookstore? Or-
Right, you get your tickets with your graduate cap and gown and all of that stuff.
Right, thank you.
So, and then you just check back at the bookstore, see if anybody's got extra tickets. You probably won't hear about that until during finals week.
Okay,
So,
yeah,
make sense?
alright, thank you.
You're very welcome. And it turns out it was the assistant to the president who had that question, answered that question. She's the one that answers what happens at graduation question. Man, are we in the home stretch? We're actually probably gonna have, a pretty relaxing day Wednesday because we're moving at a pretty good clip. Okay, because we just have to finish up the earthquake stuff. There's not a whole lot of stuff on earthquakes. Some of it is a little more detailed, like you're following along with very similar notes to Geo 110. So some of the stuff we're gonna go over very quickly. And then there's a mapping activity, and that's one of those things that it's at your own, we've already done the cookie tectonics, so you're ready for that. And that's at your own pace, and that means that if you get done faster, you get done faster. If you get done, if it takes you more time, that's groovy too. It's a review. Do you understand the homework? Do you understand what these different plate boundaries are about? Make sense? Spectacular. Let's go back. We did cookie tectonics. Let's make sure that we, it was fun. We ate cookies. We ate frosting. Let's talk about what that was actually about, what the learning objective is. Because the learning objective was not a glucose spike. Okay, that was not what we were out there to learn.
But it helped.
Huh?
But it helped.
But it helped, yeah. A little glucose spike always helps. So, so what are some of the take-home messages from that activity, from the cookie tectonics? What did you learn about? What two parts of the Earth did we focus on? Lithosphere and asthenosphere. Excellent. And what's the lithosphere?
Rigid upper layer.
Right, rigid upper layer. What parts are part of the lithosphere?
Crust and mantle.
Crust and the entire mantle?
Upper mantle.
Very upper mantle. Excellent. What's the asthenosphere?
Lower mantle.
Not quite lower mantle. Mantle below the lithosphere. So I know that sounds a little confusing when we go over the parts of Earth. When we finish talking about earthquakes, because earthquakes is how we know about the parts of Earth, we'll see a little bit better exactly how massive the mantle is. It is the bulk of Earth. Most of Earth is mantle. And which parts of the mantle actually fit into the asthenosphere. What did we learn about plates and plate boundaries?
There's 3 different kinds.
3 different kinds, excellent.
Divergent moves away from each other, convergent comes together, one subducting, and then transform is when they slide past each other.
When they slide past each other, excellent. What kind of plate boundary has trenches? Which one did we have? One cookie, a trench form between our cookies. Convergent, excellent, Caitlin. What kind of plate boundary do we see the formation of a mid-ocean ridge between our cookies? Divergent, excellent. Remember we pushed down and that caused the center to squish up. Okay. Frosting represented asthenosphere and cookie represented lithosphere. Excellent, because the lithosphere has what texture? It is rigid. Excellent. In which plate boundary type do we have lithosphere being destroyed? Convergent, right? Because that's the cookie to frosting. In which plate boundary type do we have new lithosphere being created? Divergent. Excellent. Okay. So we're gonna go backwards to earthquakes. What are the names of the 4 earthquake waves? Seismic wave types. 4 seismic wave types. P, S, L, and R. Excellent, Amber. You got it. So P, S, L, and R. Which 2 are body waves? P and S. Excellent. What does body wave mean? Passes through the earth. Excellent. Which 2 are surface waves? L and R. Do we need to know anything else about L and R waves? Nope. That's it. They're the surface waves. If you know that, you're covered. And they're slower and they arrive less. Last. What's the difference between a seismogram and a seismograph? Excellent. So a seismogram is the recording of the earthquake, and a seismograph is the instrument that actually creates the recording. So let's take a look at this seismogram that we were looking at before we had to go next door to eat the cookies. Because we cannot eat cookies in here. This is a no eating lab. So P waves are the fastest waves. So where would we expect them on our seismogram to show up when? Last? If they're fastest? First. Excellent. So the actual shape of the different the actual shape of the wave, sometimes you'll see the amplitude of the P wave bigger and sometimes smaller. But the first group of waves are always our P waves. The second group of waves are our which waves? Which waves are the second fastest? S waves. And this big group of waves over here, which ones?
There's the surface waves.
Surface waves. Oh, I was going to ask a really cool question in GO 131 related to the Alaska earthquake. Remind me, Catherine. It's a thinking question.
Okay.
So it's for review about faults and whatnot, because there was an unusual feature with the Alaska earthquake. Did everyone hear about that Alaska earthquake?
Yeah.
Yeah. One of those great cases of like, yes, I know it's a tragedy, but it's so cool, you know. Luckily, no one got killed this time, but if you look at the pictures of, for example, the Alaska highway, my boyfriend's from Fairbanks, and, originally from Chicago, but lived in Fairbanks for many, many years, and he said that place is going to get weird because the highway is utterly destroyed. And what's light like up in Alaska at this time of year? How much light do they get? Like, pretty much none, okay? So they can't, construction crews are having trouble. Everything's frozen. It's dark all the time because it's winter and we're at a really high latitude. And the roads are all destroyed, and there's only one major highway that runs from the coast all the way up through Alaska. The only other way into Fairbanks is to come up through Canada. So Fairbanks is going to have a heck of a time this winter with the highway destroyed. So P waves, S waves, surface waves. Now, some of you, we're not going to spend a whole lot of time on this. There's a little wiggle at the end. Does anyone know what that little wiggle is called? That is an aftershock. Excellent set. So this right here is our aftershock. And really what causes earthquakes is friction along the surfaces of a fault. And really what an aftershock is after that fault we have that movement, that sudden movement that causes the earthquake. Then there's still a whole lot of force, a whole lot of stress going on. And so it kind of like takes a little time to stabilize and settle into place. So those last, as it wiggles back into place into something that's a little more stable, that's what the aftershock is. I'm going to test you on it, but kind of a cool fact, because it's one of the things that we're worried about with the Alaska earthquake is aftershocks. So these are pictures of what? Seismographs or seismograms? Seismograms. Okay. So seismograms can be used the distance to the earthquake, as well as the time that it occurred. So it can determine the distance and the time that it occurred. Now I've got to find a new figure for this, because this part in here is arbitrary. We don't worry about that in determining distance. Just X it out. Imagine it doesn't even exist. In fact, in another one, I might even take clip art and scoochy things so it doesn't exist anymore. The way that we determine the distance to the earthquake and when it occurred is by looking at the time between the P and the S wave. So, question is, how does that work? Okay, how do we use that in order to determine how far we are from an earthquake? So, we're going to imagine two people running a race. We are going to imagine Usain Bolt and your professor, who is also a runner, Chris. Now, who is faster? Usain Bolt or me? Be honest. No, Dr. Evie is not faster. Come on. Bolt, no, I'm not faster. So, yeah, no, definitely not. I am enthusiastic for running, not particularly quick. So, Bolt is much faster, and Professor Evie is slower. Very slow. So which one of us represents the P wave and which one represents the S wave? Bolt is the P wave. So this is the P wave. And I will represent the S wave. So think of that while we're talking about that analogy. So at modern races, about halfway through, or actually in one of the last races I was in Syracuse, they actually had it like every 5 kilometers. It was a half marathon. They'll have timers during the race. Little bars you cross that will tell you how much time you've been running and measure it. Okay? So here, this is the start, this is the middle, and this is the end. So, at the start, air horn goes off, race starts. How much time between Bolt and I at the starting line? 0. Excellent. So there is no difference. We cross the start at the same time. The difference in time is 0. Now, it's a 5K, so we'll imagine that the 2.5K is 3.1 miles. So imagine about a mile and a half in, what's the time difference between Usain Bolt and I? Is it 0 or is it more than 0? More than 0. Okay. So here, the time between when Bolt and Chris cross the midpoint is, I am going to be, well, it's a 5K, so I'm going to be super generous to myself, is about 5 minutes. 1.5 miles. Oh, it's going to be more than that. Well, it will be nice to me. Usain Bolt is having the worst day of his life, and I am having the very best day of my life. Okay? Best running day. Now, by the end, the time between when bolt crosses and crisscrosses, bolt crosses and crisscrosses, the finish line is about what? Maybe 10 minutes, maybe about 10 minutes. So the time difference between us increases at each, increases as we get farther from the start. So when I cross the middle line, okay, the middle line, 1.5 miles, best run of my life, it would probably be at about the 10-minute mark. I cross about a mile and a half in. He's gonna get there in about 5 minutes, right? Okay. Making it to the end, we're gonna have, I might cross after about, let's say I'm running at the fastest race of my life, and I cross at about 25 minutes, and Bolt is having a really bad day. He's really sleepy and tired, didn't have his coffee, crosses in about 15 minutes. Okay, so the time between the two of us increases over time. Okay, does that make sense at least a little bit? Kind of a clunky analogy, but it works a bit. Okay, now the advantage is, unlike runners, earthquakes travel at more or less a constant speed. Okay, and we can actually plot the arrival times, or the speed between the racers, or speed between the P and the S wave, on what's called a P and S wave time travel chart. Time travel graph. Now when we're using this chart, we're looking at the time in between the two of them. The P and the S wave. Now, since I'm not going to ask you to actually do this, we're just going to cross off this section over here, okay? We're not going to actually calculate it. But just know that the big key here is more time between the P and S wave implies a further what? Distance, right? Distance from the epicenter. Make sense? Now, this is a real seismogram, okay? This is from March 11th, 2011. Anyone know what earthquake that is? March 11th, 2011? Huh? Oh my gosh! Fukushima Daiichi! Perfect, Caitlin! So this is the Fukushima earthquake. Okay, that was the one that hit, where we had tsunamis hit Japan, damage to the nuclear power plant, which led to the whole, like, why are you putting nuclear power plants in seismically active areas? Okay. Take a look at this. Looking back at our idealized one over here. Okay. I want you to try, and I recommend you do this in pencil, try to label the P, S, and surface waves on this one over here. Good. It's not gotta check, I'm just glancing over your shoulder, seeing if, excellent. Glancing over your shoulders, making sure you're picking up what I'm putting down. Awesome, awesome. Looks like pretty much everyone's got it. This guy right here, oop, I made it too big. This guy right here is the P wave. This guy over here is the S wave. And this over here is our surface waves. Now I want you to keep in mind, it is a likely test question. Is label the P, S, and surface waves, and figure out which seismogram is furthest from the epicenter. So if I had two seismograms, we'll call that A and B, and one looked like this, we have a nice clear P wave, and then a nice clear S wave, and then some surface waves. And in B, we have a nice clear P wave, and then a nice clear S wave, and then some surface waves at the end. Which one, A or B, is closer to the epicenter? B, why?
Because they're closer together.
Excellent. So here we have the P and the S. P, S, P, S. Here the P and the S are closer. So B is closer than A to the epicenter. Not the best grammatical construction, but you got my point. Now, why does this tell us anything about the inside of the earth and the shape of the earth and that kind of stuff? We're going to look at a really simple example that's a little bit like the X-ray we talked about. Remember when we were talking about X-rays and passing through? And use it as an example for how do we determine what's going on inside the earth when we've never been deep down in there. So, waves tend to travel faster in less dense and more, and we're going to X this out and say rigid substances, because the term elastic means something slightly different in physics than it does in everyday English. So we're going to say faster and less dense and more rigid substances. So these changes in speed make waves bend, and what's waves bending called? Refract, excellent. Or bounce, which is? Reflect, excellent, Catherine. Reflect. Now, from looking at those changes in wave speed, we can determine what the composition is, or at least what the material properties, how bendy it is, how squishy it is, how dense it is, of the materials on the inside of the earth. Now if we look here and we're watching, this over here is our P wave, or I'm sorry, S wave, and this over here is our P wave, right? What do we notice down here in the area labeled the outer core?
No S wave.
No S wave. So excellent, Leilani, this section in here has no S wave. And this gets into what I think is an awesome and interesting story of science and a little bit of a simple example of how we use earthquakes to determine what goes on inside of the earth. So, let's suppose that we have This is the Earth, and we have an earthquake over here. Okay, earthquake. There we go. Need an A on that. So earthquake over here on this side of the Earth. What kinds of waves will be generated? P, S, L, and R. Excellent. So P and S waves and surface waves. Now, are the surface waves going to go through the Earth? No, they're just going to go over the surface over here on the surface. So we're not going to worry about them. We're just going to worry about the P waves and the S waves. So let's suppose I have directly opposite of this, I have 3 seismograph stations. We'll call them A, B, and C. And we'll have solid line indicate P waves and the dotted line indicate S waves. So if I have an earthquake over here, I will have a P wave, and a P wave show up at A, B, and C. Okay, so that means that the P wave is traveling through the Earth, curves